Hey, welcome back to Abstract Algebra. This is the first lecture of the material I want to cover with you guys in section 2.7. It's about something called the First Homomorphism Theorem. It's also sometimes called the Fundamental Homomorphism Theorem. This section has two other, the second and third homomorphism theorems. We will omit them from this course, but if you are interested in them, you want to read about them, I'm happy to talk about that kind of stuff. But in this lecture, I have two goals. And they are to, well, state this theorem, state the first homomorphism theorem, and then give its proof. So that's going to be it. It's a very focused video lecture. And then in the next one, we'll take a look at how you can use this theorem to find out what the structure of a factor group is. All right, so let's just get started. In order to state the theorem, let's set a little background here. We'll give ourselves a homomorphism called phi. From a group G to a group H. I'll be writing these groups multiplicatively. And let's go ahead and denote the kernel of this homomorphism by short by just the letter K. And we'll recall that since it's a kernel of a homomorphism, it's a normal subgroup. All kernels of homomorphisms are normal subgroups. All right. Good. Recalling a little bit further, if you have a normal subgroup, then the set of its left or right, doesn't matter which side you want to say it, subgroup, or cosets rather, excuse me, are they form a group. It's called the factor group of G mod K. It's how we'll pronounce that, or G over K if you want to say it, but we know it's a group because K is normal. All right, one more thing I want to recall. I think this was back when we were still talking to each other in person. That given this group homomorphism phi, if you pick an element A in the group and you take phi of it, I'm going to kind of do this inside out, and then you can ask yourself the question, well, what other elements in G map to the same place that phi mapped A? That is, you look at the inverse image of that singleton set that has phi of A in it. And we proved on the blackboard that that inverse image is exactly the left coset containing A, or right coset if you want. It's a normal subgroup. All right. So it's kind of an important property that if you take an element in a group, you look at its image under a homomorphism, the other elements in the group that map to that same place are exactly the coset of the element that you picked, the coset mod the kernel. Okay, an important fact. Saying in another way, this is just a summary of it. The cosets in G mod K correspond, one-to-one correspond with points in the image. You give me a coset, it corresponds to this point phi of A. And what's A? A can be any element of that coset. So it kind of hints at the theorem I want to try to state, that the set of cosets, this factor group, it's in one-to-one correspondence with the image of G, another group. And well, you have two groups that have a one-to-one correspondence between them, they have a chance of being isomorphic. And in fact, this first isomorphism theorem exactly says that they are. All right, so let's state this theorem. It is quite a mouthful, but let me try to walk you through it. Its number in our text is theorem 2.71. All right, it's called the First Homomorphism Theorem, or FHT, if you like to, for short. So here's the statement of it. You have to be given a homomorphism, and it needs to be onto H, okay? I'm just gonna kind of hit the high points of this. So I'm given some homomorphism, it's onto its image, H, or its codomain. We'll again let K denote its kernel, and then here's the statement of the theorem. The function from G mod K to H that's defined by sending a coset AK to phi of A, and that's for every coset in the factor group, that function is well-defined group isomorphism, and it satisfies this equation that phi will be the composition of eta and it, where eta, remember, is our canonical homomorphism, the homomorphism that sends a group element to the coset that contains it. Okay, so that's a lot to unpack. It's a lot to unpack. What is this theorem saying? That this certain function is defined by a formula given in the theorem. We're supposed to prove that function is a group isomorphism that satisfies a certain equation. Okay. Why well-defined? Well, because psi is doing something to a coset, AK, and that action is done in terms of the representative, phi of A. Well, AK, the coset containing A, has many representatives. And so that's why we have to worry about this well-defined business. What if somebody used a different representative for the coset AK? What if they used alpha? Then they're going to say that psi of alpha K is phi of alpha. We need to make sure that phi of alpha and phi of A are the same. Okay, let's start taking a look at the proof. First order of business is this well-defined. If that function is not well-defined, I don't think there's any reason that we should prove any other properties about it, because we should just put it in the trash. I just answered the question, why do we need to show this? We need to show it because psi is acting on a coset by doing something to its representative, and there's many representatives. All right, so here, let's try it. Take two elements of this group G, A and B, and let's suppose that they represent the same coset. Okay, so the coset containing A and the coset containing B are the same. Let's walk through these inequalities, or these implications, double implications. The first one, that's the definition of coset inequality, or coset equality. Sorry, my tongue is tripping. Two cosets are equal if and only if the product of the representatives is in the subgroup with the inverse on the left. These are left cosets. The second one, I'm just remembering what K is. K is the kernel of phi. So if B inverse times A is in K, well, that means phi of it is the identity. And I'm just putting a little subscript on the E there. It's the identity in H, the identity in the codomain. All right. And now some homomorphism properties. Phi of B inverse A, well, that's phi of B's inverse times phi of A. Phi is a homomorphism. And then just multiply both sides of that equation. Now I'm working in the group H. Multiply that, both sides of that equation on the left by phi of B, and you get this. All right. So each one of those implications, those if and only if statements, is explained, and then let's see what we can get from them. If you look at the ones that are only pointing to the right on your screen, the implications that are all kind of the ifs, they exactly show that psi is well defined. Yeah? Why is that? Because I'm just going to look at the very first one and the very last one. It says that if the cosets containing A and B are the same, then, well, phi of A is psi of AK, and phi of B is psi of BK. So if the cosets are the same, then psi of them is the same. Psi is well defined. It's a little bonus of our work here that the other implications, we don't have to throw them away. They exactly show that psi is 1-to-1, right? Again, starting on the far right of your screen, the underlined phi of A equals phi of B. Well, that just means this. If psi of AK is psi of BK, all those things end up saying, well, AK is BK. So psi is a function with the property that if two of its outputs are the same, its inputs have to be the same. That's exactly what we mean by a 1-to-1 function. So this is good. A good deal of our work is done. We've got a well-defined homomorphism, or sorry, a well-defined function that's 1-to-1. Is it? Let's make a list. What else do we have to show here? We need to still worry about it being onto. We haven't shown that psi is a homomorphism yet, and then we haven't shown this equation about the way these things compose together. So let's do it. Let's do the onto part first. How does an onto proof start? Pick an element of the codomain. Codomain of this function phi, of psi, or excuse me, is H. So pick an X in H, right? And I want to try to find a coset that maps to it. How am I going to do that? Well, the function phi that we're given in the statement of the theorem, it is onto H. Phi is onto. So you give me some X in H, I can find an element in the group G that phi will map to X. Yeah, and that element in the group G, it's got a coset. It's got a coset. Every element in G has a coset. And by definition, if we take psi of that coset, we get phi of A, so we get X. So psi is onto. Psi is onto because phi is. Nice. All right. What about homomorphism part? Let's pick two elements of the domain. Let's show that psi has this homomorphism property. Let me just bring it up here in the middle of the screen so you can look at it. So what am I doing? I'm picking two elements of the domain and I look at psi of their product. All right. Well, psi of their product. I don't know how to take psi of something until it's a single coset, but the coset containing AK and the coset containing BK multiply together to give the coset containing AB. Yeah. And now that that's in that form, I can say, well, psi of it is phi of AB. But phi is a homomorphism, so that splits apart. And then using the definition of psi again, I get that that's psi of AK times psi of BK. So psi is a homomorphism. I sound like a broken record, but psi is a homomorphism because phi is. I mean, psi is basically just defined in terms of phi. We're just doing it cosets at a time. Nice. All right. So we've got it. Homomorphism. What was our checklist? Let me look at it again. We got onto. We got homomorphism. We got to just show this last equation that phi is psi composed with eta. All right. Well, you want to show two functions are equal. There's really only one way to do that. You have to just show that they do the same thing to every element of their domains. So let's pick an A and G, and let's run it through this composition. I'm looking at psi composed with eta of A. Well, by definition of function composition, that means plug A into eta and then plug that into psi. Eta is the canonical homomorphism. Eta just sends A to its coset. The psi of a coset is phi. So at the end of the day, what have we shown? Shown that the function psi composed with eta and the function phi do the same thing to everything in their domain. That's exactly what it means for two functions to be equal. That's it. That concludes the proof of the first homomorphism theorem. Again, it's quite a lot to unpack the statement of it. These proofs are going so smoothly because we have so much machinery behind us. We know so much about cosets and the way these things work that really all these definitions have been cooked up, that the proofs really aren't the issue. It's developing the statement of it that is the work. I'm going to end this short lecture with a picture of what this theorem says, a so-called commutative diagram. Algebraists love to draw pictures like this when we're trying to understand how functions compose with each other. And maybe also because, as I've lamented before, there's so few pictures in algebra that we like to draw what we can. So this is called a commutative diagram. Let me just walk you through kind of what I'm trying to say here. Lots of it is written in black. The stuff that's written in black was the given. Those things are given. So I'm given this homomorphism phi from G to H. So instead of writing that typical function notation, I'm just writing an arrow from G to H and writing the name of the function above it. It's kind of an equivalent way of saying that phi is a function from G to H. And we're in a group theory course. In a group theory context, it would be a group homomorphism that G and H are. And it's not written here, but it's onto. We were told that. Let me just sort of write it in there if I can neatly. Phi is an onto group homomorphism, right? We weren't really given eta, but I wrote it in black because it's always the same. It's the canonical homomorphism. Every subgroup, every normal subgroup comes with a canonical homomorphism, the homomorphism that just sends an element to the coset. Yeah, so we're not given it in the statement of the theorem, but it's always there. And then what the theorem concludes is that there's this function psi from the set of cosets to H that's an isomorphism. I'm indicating that this is typical in diagramming. They just draw a little kind of pseudo isomorphism symbol over the arrow. So it's just a visual way of saying that that's a one-to-one onto group homomorphism. And then this equation, psi composed with eta is equal to phi, or I read it kind of from right to left, phi is equal to eta composed with psi. That equation in the picture is what this little circle means. This is a so-called commutative diagram. Commutative diagram in the following sense. Let me kind of just try to do it with some color as we go here. Starting at G, there's two ways to get to H in this diagram. Now, there's two ways to move, if you like, from G to H. One way is to take phi, go straight across. You can get from G to H by taking phi. A second way is to first do eta then do psi. Yeah, that's exactly what this composition means. First do, oh, look at that. It's never happened to me before in my life. I've made a mistake. That composition is written backwards. Let me see if I can fix it here. Because the function that goes first is eta and then psi. Sorry about that. So eta, then psi. Maybe I should try to salvage this and say, see how handy commutative diagrams are? It caught my typo. Looking at the diagram, to get from G to H, I certainly have to do eta before psi. I had written it the wrong way. All right, good. Well, that makes this video a little bit more authentic. Cool. So that's the kind of pictorial version of the fundamental homomorphism theorem, that this phi can be broken down into the composition of eta and psi. Sometimes people will pronounce that broken down. I have to wait for my message to go away. Complicated world. Sometimes people say the homomorphism phi, quote unquote, factors through G over K. It factors in this sense. I've written phi as a product in the sense of a function composition of two other functions. So if you've been wondering, and I hope you have, why this set of cosets, why is it called a factor group? What does that even mean? This picture is why it's called a factor group, because the homomorphism factors through the quotient group by its kernel. All right. I'm going to stop this video here, trying to keep these things short and focused, but just to tell you what's going to go on next time. What is going to happen next time? I'd like to use the first homomorphism theorem to classify factor groups. So what do I mean by that? The fundamental homomorphism theorem gives me a chance of proving that a factor group is isomorphic to something. So in that previous lecture where I was showing you some examples of computing factor groups, often those examples ended with me saying something like, oh, I think this factor group feels like it's isomorphic to this. This tool, this first homomorphism theorem, is the tool we're going to use to prove that stuff. Okay, so thanks for listening, and I will see you soon.